Hi, in this lesson I want to talk about some of the theory behind radiometric dating. Now there's no specific handout for this, although there is a PDF of some of the graphs that I show included with this. I should apologise before I start about some of the poor geo jokes that this video is going to contain. Okay then, let's go. So far we've been looking at how we can establish the relative age of a rock. How old one rock is, or one of geological event is, relative to another. Now that's all very well, and it's the type of dating that we can do, for example, in the field. But if we want to establish timescales, if we want to establish exact points in time where these events occur, we need something that's going to put a number on a rock. And that's what this is all about. How can we actually quantify the age of a rock or a geological event? Now, with the geological timescale, we can establish the age of these particular events. And this is something that's been refined continuously over time. If you check these dates out, you'll see, for example, that there's some variation between these and the ones that you have in your timescale. But we can get an idea of how long in the past things were. For example, the base of the Cambrian, a really important point in geological time, is dated maybe about 535 million years ago now. So a timescale established by relative dating is now quantified using radiometric dating. Now, to establish a timescale, we need a clock in a rock. We need something that we can measure that changes solely as a result of the elapse of time. And what we have for this is radioactive decay. Because radioactive decay occurs at a known rate and a constant rate. Those two things are key. It's not affected at all by heat, pressure, really anything else other than the elapse of time. So if we can find a radioactive element that was incorporated into a rock when it formed and then has decayed over time, turning from what we call a parent isotope, so a parent element, which is unstable, which then changes and becomes a daughter element, something else, something different, we can measure the amount of those two elements and establish the time between when we take that measurement and when that rock formed. So for example, rubidium 87 is radioactive. When it decays, it produces an isotope called strontium 87, which is a stable one. So if we can establish the ratio of rubidium to strontium within a rock, we can establish how long that process has been going on for. Now there are a couple of other, rubidium strontium is not one of the techniques we need to know. Other ones we do need to know, carbon 14, which decays to nitrogen 14. That has some limited geological applications, although it's the one that most people know. People have heard about carbon dating, but as we'll see, carbon dating is very limited in its use in geology. Perhaps far more commonly used, and one we do need to be aware of, is the decay of potassium-40 to argon-40. And it's that we're going to explore in more detail in this lesson. So, we start with a radioactive parent atom. A nuclear particle is released, and we end up with this daughter atom, which is something different. So we get two isotopes that will tell us the age of a rock. Now, the rate this happens is what we call a half-life. A half-life is the time it takes for half of the parent atoms that we start with to decay into daughter atoms. So, the example I've given you on the diagram here, uranium. Isotopes of uranium decay to form lead. So the yellow circles there represent uranium, the blue ones represent lead. After one half-life, which for this particular atom is about 1 billion years, what we'll see is half of those uranium atoms have decayed to form lead. So what we end up with after one half-life is 50% uranium and 50% lead. We now have that 50% lead. After another half-life, half of that will have decayed to lead. So after two half-lives, we have 25% of our original parent atoms left, and 75% of them will be the daughter atoms. After three half-lives, we lose another half of those uranium ones, and we end up with 12.5% of the original uranium atoms, 87.5% of the daughter ones. So because this ratio between the two is constantly changing, if we can measure that ratio, we have a life, or we have an age, should I say, of that rock. Now this decay, this change from parent to daughter, happens on what we call this decay curve. So and every radioactive element decays on a curve similar to this. Notice there are no numbers on this. Okay. We start with N0, which is our number of original parent atoms. By the time we get to N0 divided by 2, we've been through one half-life. Let me illustrate this with perhaps a bit more clearly. So we start with 100% of parent atoms. After one half-life, we have 50% left. Two half-lives, 25% of those original parents. Three half-lives, 12.5. Four, 6.25%. And after five half-lives, we're down to 3.125, 3.125% of a percent of the original parent atoms. And because they always decay on this curve, it's very easy for us to, if we measure the ratio of parent to daughter, we can then read from the vertical axis across to our decay curve, and then down to time, which is the horizontal axis here, and work out how long this process has been going on for. The key difference between the different elements that we use is the length of that half-life, how long that actually takes to occur. Let me show you some examples. Here we see decay curves, which are the red lines represent the parent atoms, the green lines represent the daughter atoms. Now these look different shapes because in this case, rather than just plotting half-lives, we've actually plotted the amount of time in millions of years. If we plotted all these graphs in half-lives, they would all look identical. So the half-life is where we see 50% parent, 50% daughter. So it's where the lines cross. So in the top left, we've got an example here of uranium-235, which has a half-life of 713 million years. What I'd like you to do is have a look at the graphs on the PDF. Can you work out what the half-life of these other radioactive elements are? Uranium-238, rubidium-87, and carbon-14. Notice the units are different for each of these. See what you can work out. Okay, let's have a look at what you've come up with. For U238 there, a half-life is 4,500 million years, which means that some uranium-238 formed when the Earth was formed would have been through about one half-life up till now. An element does not have to go through a complete half-life for us to be able to use it. Okay, as long as we can measure the ratio between the parent and daughter, we can measure the age of the rock. U238 is a very good element for dating if it's contained within a rock because of that half-life. Rubidium strontium has a significantly longer half-life. That's about 47 billion years. So rubidium strontium might be better suited to dating ancient rocks rather than perhaps more recent rocks where we measuring the exact amount of parent and daughter might be quite tricky. And finally, carbon-14. Carbon-14's half-life is a very specific 5,730 years. This is why carbon-14 has very limited geological uses, because its half-life is so short. By the time we've been through about 8 half-lives, there's virtually nothing left. And 8 half-lives for carbon-14 takes us to about 50,000 years. It's really a very, very short period of time. So its geological use really is limited to the very end of the Quaternary period. Anyway. So there are these different elements that each have different uses for dating. We talked about some of these already, but there are 2 key ones that we need to know. We have potassium argon. I apologise for the mistake in the symbol for the daughter atom there. Potassium argon has a half-life of about 1,300 million years. Quite a useful half-life. So it can date a range of rocks from about 50,000 years ago up to the formation of the Earth. And we find this potassium 40 in some micas. We can find it in hornblende and volcanic rocks in general. There are some issues with potassium 40 to argon 40. For example, potassium is quite a common element in orthoclase feldspar, but we cannot date orthoclase feldspar using potassium argon because of the problems with the daughter element. The daughter element here is a gas, which means that it can leak out the rock. And in feldspar, because of its cleavage, the argon will leak, and it gives anomalously young dates for the rocks. It's the major limitation of potassium argon dating. The other one we need to know is carbon dating, but I'm not going to talk too much about that at the moment. It's extremely useful for dating biological material. We can date fossils with it. We can date carbon dioxide with it, which is useful in terms of climate change data. But its useful range is very, very limited. At the absolute most, and really squeezing it hard, you can get back about 70,000 years. It's really not very long. But potassium argon then is the main dating technique I want to talk about today. So we have our parent atom on the left there. As I said, it's found in mica, clay mineral, tephra, which is volcanic ash. And we can use that then by measuring the proportion of this potassium 40 to argon 40 within these particular rock types. It's important, and one of the things we need to be able to do is to assess the usefulness of these dating techniques. So you do need to think carefully, what are the key strengths of potassium argon dating? From what I've said already, what do you think these might be? And what's the limitation? What's the problem with potassium argon dating? What have we got to be very careful of? Okay, you need to know this. You can be asked to evaluate a date based on the technique that was used to measure it. Now, this technique is very widely used. Back in 2013, this was the first dating method used to establish a radiometric date away from this planet. You know, we dated rocks that have been brought back to the planet, but in 2013, Curiosity rover was able to actually measure a date of a rock on another planet. I've given you a link to listen to an interview with a geologist from Caltech talking about dating these rocks. After this lesson, listen to that audio extract. It's fascinating. So, we've identified some limitations here. Potassium argon is a potentially flawed method, particularly because of this daughter product being a gas. We can end up with anomalous dates that are inaccurate and inaccurately young, because if we lose daughter elements, it looks like there's a greater proportion of parent, so that'll give us a younger age. Now, to get round this, new dating techniques have been developed. In particular, a dating technique that's based on isotopes of samarium and neodymium. But that's the topic for another lesson. So, as we watch a representation of the sun setting on Mars, and conclusions there in Klingon, because it's the closest I could get to Martian, let's sort that out. These radiometric dating techniques are crucial in geology. It's how we establish real, actual timescales. But with the application of any of these techniques, we must be aware of their limitations. We must be aware of the errors that are potentially in these dates, and to be able to account for those errors. Next time, we need to look at a newer version of radiometric dating, one that potentially could give us more reliable, more accurate dates. But that's for another lesson. I'll see you then.